Senior High School General Mathematics Core Subject. General Mathematics includes the study of functions, business mathematics, and logic. Functions. Learning goals. At the end of the lesson, the student is able to represent real-life situations using functions, including piecewise functions, and solve problems involving functions. Function. Function is a relation where each element in the domain is related to only one value in the range by some rule. The elements of the domain can be imagined as input to a machine that applies a rule so that each input corresponds to only one output. A relation is a rule that relates values from a set of values called the domain to a second set of values called the range. The elements of the domain can be imagined as inputs to a machine that applies a rule to these inputs to generate one or more outputs. Functions. The input process output or IPO model is an approach used generally in information processing and many other processes. Mathematical functions can also be modeled by the IPO approach, where valid inputs are processed by defined operators to produce outputs based on these operators. To illustrate, the figure below shows the IPO process applied to taking a photo or document and have it printed. The input would be the screenshot of the document or when the photo is taken. The process involves all necessary procedures prior to printing, which may include editing, cropping of pictures, transmission of data from the phone to the printer, etc. The output is the actual printed photo or document. The function as a machine. Mathematical relations can be represented as processing machines with an input and an output, and that the output is related to the input by some rule. Consider the following illustrations. Let's say we have a machine labeled below as machine A that accepts any letter of the English alphabet as inputs. Suppose this machine processes a random selection of these letters. We do not know yet the rule to which the machine prompts to generate the output, but let's say that the machine selects the letter L. The machine then produces the output 21. The rule that the machine follows is not yet clear at this point, but let's try another round of selection. This time, the machine selects the letter E and produces the output 5. Now, the rule is seemingly becoming clearer now. But let's try a few more rounds just to make sure. For this round, machine A selects N and produces the output 21. For this round, machine A selects the letter U and produces the output 5. It is now clear that the rule that the machine employs in order to produce the output is whenever the machine selects a vowel of the English alphabet, the output then is the number of vowels. Otherwise, if a consonant is selected, then the output would be the number of consonants. Let's consider another machine. This time, machine B, which accepts the numbers 1 to 10 as inputs. Now let's try to see what machine B does. What machine B does is that it makes use of this spin wheel in order to make a selection of these numbers. Let's have it a go for a spin. When the number 10 is selected, machine B produces the output 100. When the number 6 is selected, machine B produces the output 36. Let's try one more. When the number 4 is selected, machine B produces the output 16. From these results, we can fairly say that the rule that machine B employs is that whenever a number is selected, it squares that number. Let's have some further examples. Shown below are machines labeled A to F, of which machines A and B were already described in the previous examples. For machine C, it's a machine that accepts any letter of the alphabet or any number from 1 to 26 as inputs. For its output, machine C either selects any letter from A to Y and generates the next letter, or if Z is chosen, then it generates the output A. Or if a number is chosen, then the letter corresponding to that number will be its output. Next is machine D, which accepts any two-dimensional image and generates a rotated image 15 degrees clockwise. Next is machine E, which accepts any real number and then generates either the number itself or the number is negative. Finally, we have machine F, which accepts any non-zero rational number and generates the output, the reciprocal of that number. To further illustrate the idea of a function as a machine, let's try to reflect and analyze the following questions. First, which of these machines, if you know the input, can you determine a single or unique output? I suggest that you pause the video and analyze each machine before I reveal the answer. For the answer, all of these machines produce a single or unique output except for machine E. Why? Because machine E may have an input, say -2, and produce an output of the number itself, or the number is negative, which is one and the same, and therefore not unique. Next question is, we ask, which of these machines, if the output is known, can you determine a single or unique input? Again, I suggest that you pause the video and analyze each machine before I reveal the answer. For the answer, only machines D and F qualifies as if we know the output, can we determine a single or unique input. Taking a look at machine D, the output is a rotated image of its original image. Its original image is the same image but previously not rotated, and therefore is unique, since we consider every picture taken as a unique moment in time. The same goes with machine F. Having the reciprocal of a number means that we can find its previous non-reciprocal form, which is unique for every rational number. While the rest of the machines do not qualify as having unique inputs, taking a look at machine A, for instance, if we know the output, say 5, can we determine a single or unique input? The short answer is no, since we can have several inputs to produce the same output 5. Suppose we connect machines A with machine C, so that the output of A becomes the input of C. Give the outputs for the following inputs, A, R, S, and U. Again, I suggest that you pause the video and analyze the machines before I reveal the answer. For the answer, first we have A as input to machine A. Machine A then produces the output 5 for vowels. 5 then serves as an input to machine C. 5 being a number, points then to the output as the letter corresponding to that number. So 5 is for E. Next is R, a consonant. Therefore, the output of machine A is 21. 21 as an input for machine C gives the letter U. Given these, you can then work out the rest of the results. Functions and relations as a set of ordered pairs. A relation can be expressed as a set of ordered pairs between the elements of its domain and the elements of its range. Let's try to define what a domain and a range is. A domain is the set of all possible values of the variable x can take in a given relation, while the range is the set of all possible values of the variable y can take in a given relation. If we let the set capital X as the domain and the set capital Y be the range, then a relation can be written as the set of all ordered pairs xy, where small letter x are values in the domain of capital X and small letter y are values in the range capital Y. A function is the set of ordered pairs xy such that no two ordered pairs have the same x value. Let's have several examples to illustrate this definition of a function. Which of the following relations are functions? Set f, g, and h. Before I reveal the answer, I suggest that you pause the video and analyze these sets and identify which of these are functions. For the answers, set f is actually a function. Set g is not a function, while set h is a function. Since the function is the set of ordered pairs wherein no two ordered pairs have the same x value, we can see that only set g is disqualified from this definition, since it has the elements 1, 3 and 1, 4 in the set of ordered pairs. Mapping diagrams. Relations and functions can be represented by mapping diagrams, where the elements of the domain are mapped to the elements of the range using arrows. In this case, the relation or function is represented by the set of all the connections represented by the arrows. Which of the following mapping diagrams represent a function? Let's say we have a set X with the elements 1, 2, 3, 4, and 5, and a set Y with the elements 3, 5, 9, 17, and 33. Now suppose the elements in X are mapped to the elements in Y as shown. Let's call this relation F and list down all the ordered pairs as a set based on this mapping diagram. Let's have another pair of sets X and Y. This time, set X has the elements 5, 6, 7, 8, and 9, while the set Y has the elements 0 and 1. Now suppose the mapping goes as shown. Let's call the relation between X and Y this time as G and list down all the elements based on this mapping diagram. Finally, for this example, let's have the last pair. This time for set X, we have the elements 7, 2, and 1, and the set Y with the elements 11, 13, 17, 19, and 23. The mapping this time between X and Y is as shown. Let's call the relation between X and Y this time as H and list down all the elements of this mapping diagram. As before I reveal the answers, I suggest that you pause again the video, analyze the sets, and determine which of these relations are functions. Since the definition of a function is the set of ordered pairs xy, where no two elements of the set have the same x value, we can see that f qualifies to be a function. The same goes with g, but not h, because h has the elements 217 and 219, as well as the elements 711 and 713. In terms of mapping diagrams, a relation would be a function if each unique element in the domain X is mapped to each unique element in the range Y, just like in the case of the relation F. Now, any element in Y can have more than one element in X mapped onto it and still be considered as a function, since this would still qualify as having a unique X value, such as in the case of the relation G. H, on the other hand, do not qualify as a function since some of the elements in X is mapped to more than one element in Y, creating ordered pairs with non-unique X value. Functions as a graph in the Cartesian plane. Recall that a relation between two sets of numbers can be illustrated by a graph in the Cartesian plane, and for such a relation to be a function, it must pass the vertical line test. A graph represents a function if and only if each vertical line intersects the graph at most once. This is the vertical line test. Let's illustrate this idea using several graphs as examples. First, say we have this sine wave as a graph. Now the question is this a graph of a function? Using the vertical line test, by dropping several lines, we can see that each line intersects the graph at most once anywhere on the graph. Therefore, this graph is a graph of a function. Next, we have the graph of a circle. Using the vertical line test, we can see that this vertical line passes the circle at 2 points. And hence, this graph is not a function. We can also see that since the points of intersection of the vertical line and the circle have the same x value, therefore this disqualifies it to be a function. Next, we have this diagonal line, which qualifies as a function. Next is a graph of a parabola, which is also a function. Lastly, for this illustration is a graph of a horizontal hyperbola, which is not a function, since the vertical lines can pass through the graph either twice or none at all. Example: which of the following represents a function? Identify the domain for each relation using set builder notation. Letter A, y equals 2x plus 1. Letter B, y equals x squared minus 2x plus 2. Letter C, x squared plus y squared equals 1. Letter D, y equals square root of x plus 1. Letter E, y equals 2x plus 1 all over x minus 1. Finally, letter F, y equals the floor function of x plus 1. The floor function is also called the greatest integer function. Let's try to define this function. The floor function, also known as the greatest integer function, denoted by this symbol, is the function that takes any real number x as its input and gives an output of the greatest integer less than or equal to x. There is also called a ceiling function, also known as the least integer function, denoted by this symbol. The ceiling function is the function that takes any real number x as its input and gives an output of the least integer greater than or equal to x. For the answer, in all the above relations, i.e. functions, only C is not a function. Since if we try to manipulate the equation in letter C, we have x squared plus y squared equals 1. Solving for y squared gives us 1 minus x squared. Taking the square root and then substituting the value 0 for x squared, we have 0 squared, which leaves us y equals square root of 1. Extracting the root should give us y equals positive or negative 1, which implies that the set of the range y includes the ordered pairs 0, 1 and 0, negative 1, which have the same x value. Therefore, this disqualifies C as a function based on the definition. As for the domain of each of the given relation, we have the following. For letter A, letter B, and letter F, the domain is the set of real numbers. While for letter C, we have the closed set from negative 1 to positive 1. For letter D, we have the set which includes negative 1 up to positive infinity. While for letter E, the domain includes the range negative infinity to 1, union 1 up to positive infinity. Functions as representations of real-life situations. Functions can often be used to model real situations. Identifying an appropriate functional model will lead to better understanding of various phenomena. Example: give a function c that can represent the cost of buying x meals if one meal costs 60 pesos. Solution: since each meal costs 60 pesos, then the cost function should be c of x equals 60 times x. Example: 100 meters of fencing is available to enclose a rectangular area next to a river. Give a function a that can represent the area that can be enclosed in terms of x. As a solution, let's say that this is our rectangular fencing. The rectangular fence has the width x and the length y. The area of the rectangular enclosure is therefore A equals x times y, whose length of fencing is 100 meters. We can write therefore x plus twice of y, which is equal to 100, and re-express this in terms of x. We substitute the result in a function of x. Writing down the solution, we start with x plus 2y equals 100. We transpose x to the other side, making it negative, then dividing both sides by 2, distributing the denominator 2. Then we have y equals 50 minus 1 half x. We substitute this result in a function of x, giving us a of x equals x times 50 minus 1 half x. Distributing x, we have 50x minus 1 half x squared. Piecewise functions. Some situations can only be described by more than one formula, depending on the value of the independent variable. Example, a user is charged 300 pesos monthly for a particular mobile plan, which includes 100 free text messages. Messages in excess of 100 are charged 1 peso each, represent the amount a consumer pays each month as a function of the number of messages M sent in a month. Solution. Let T of M represent the amount paid by the consumer each month. It can be expressed by the piecewise function T of M equals 300 if M is greater than 0 but less than or equal to 100, or T of M equals 300 plus M if M is greater than 100. Example, a jeepney ride costs 9 pesos for the first 4 kilometers, and each additional integer kilometer adds 1 peso and 50 centavos to the fare. Use a piecewise function to represent the jeepney fare in terms of the distance d in kilometers. Solution. Let f of d represent the jeepney fare paid for the distance d of the ride. It can be expressed by the piecewise function f of d equals 9 if d is greater than 0 but less than or equal to 4, or f of d equals 9 plus 1.5 times the floor function of d if d is greater than 4. Now take note that what the floor function means is that the passengers pay the fare for integer values of distances beyond 4 kilometers, even though the actual distance traveled have some decimal or fractional component. Say a passenger rode a jeep and traveled a distance of 14.8 kilometers. The passenger would then pay an amount of 9 plus 1.5 times the floor function of 10.8 equals 9 plus 1.5 times 10 equals 24 pesos. Example, water can exist in 3 states: solid ice, liquid water, and gaseous water vapor. It takes a certain amount of heat before water can change state. Use the following information to sketch the graph of the function representing the temperature T of water as a function of the amount of total heat Q added in joules. Explain why this is a piecewise function. At this point, I suggest that you pause the video and list down the descriptions below for your reference in constructing your graph. For keynotes, the phrase "the temperature remains constant" or "the temperature stays constant" translates to a graph of a horizontal straight line. Another note is that the phrase "the temperature increases steadily" translates into a diagonal line sloping upward. For the solution, you should be able to sketch the graph similar to this one. Now we'll let T of Q represent the temperature of water in degrees Celsius as a function of the cumulative or total heat Q added in joules. This function is a piecewise function because the temperature behavior is different across a sequence of intervals.